Morning, everyone. I'm Gus Lehrer, and this is the beginning of my second lecture, the second lecture in my series of 3 on invariant theory, classical, super, and quantum. Without further ado, I'm going to share my screen. In the last lecture, we discussed classical invariant theory, mainly of the general linear group, and we gave some background about the Brauer category and how it can encode quite a high degree of complexity among morphisms. And now we're going to see how to make use of those concepts in the invariant theory of the isometry groups of forms, once again in the classical context to begin with, and later in this lecture we'll move on to the to the case of supergroups. We have TG of V, that is the tensor category of it's the full subcategory of the representations of G, whose objects are the natural module V, taken to the rth power, where r is 0, 1, 2, and so on. And we have the usual tensor product of modules and G module homomorphisms, and that makes that into a tensor category. I just better make a note of the time. Now we want to study this tensor category, and in particular we want to study the representations which constitute it, initially in this context of the base ring C, which is a classical case, and notwithstanding what people may think, there are still actually some mysteries even in connection with that case. For example, closed formulae for the multiplicities are not known. There is some work of physicists, but as far as I know, that is equivalent to the study of dimensions of some non-semisimple representations of Brauer algebras, as we shall see. Now, remember this element C0, which is called a Casimir element. It's G invariant, and it's G invariant of the tensor square, and we make use of it by, or Brauer made use of it by saying there is a, he didn't exactly put it this way, but what he proved was equivalent to this, that there is a unique covariant functor of tensor categories between the Brauer category over C with parameter epsilon m. You'll remember how that arose. It's epsilon times the dimension. Epsilon is +1 in the orthogonal case, -1 in the symplectic case. Defined by on objects by saying that f of r is the tensor power. To define it on morphisms, you'll remember that I pointed out that there are 4 morphisms, namely these, which generate all morphisms in the Brauer category. So we need to define this functor only on these. F of I is the identity. F of x is the interchange, but with a sign of A. That means f of the cap is given just by taking of the inner product. Finally, f of u is a map from v tensor to the 0 to v squared, and that's given by taking 1 to this special element C0. Brauer actually proved in his 1937 paper, which really didn't attract much attention for about 25 years. He proved that this was a functor. And he furthermore proves that this functor is full. So the functor induces surjections on the Hom spaces. We saw last time that the Hom space from T to the RV to T to the SV depends only on R plus S, and similarly the Hom space in the Brauer algebra depends only on R plus S, and so it suffices to prove it for R equals S, which is what Brauer did. We've seen the result of Juin and Chaire that the Brauer algebras BR of M and BR of -2M, where M is a positive integer, are both semi-simple precisely when R is greater than or equal to M plus 1. And therefore, the implied surjective map, which we have from the Brauer algebra to the endomorphisms of this tensor power, has to have image, which is a semi-simple algebra. But since BR of epsilon M is not semi-simple, once R is at least M plus 1, we know that there must be a kernel, at least for most of the values of R. A recent result, which has been recast in many different ways, proved by myself and Ruben Zhang, first in 2012-13. Let's write D for M if G is O of V, where V is the dimension of M, and it's the dimension of V, and dimension of V divided by 2 if G is the symplectic group. Then the kernel of the map eta R, that's this one here, from the Brauer algebra to endomorphism space, to the endomorphism algebra. This kernel is 0 if R is less than or equal to D. If R is greater than or equal to D plus 1, the kernel is actually generated by a single idempotent in this Brauer algebra, which is explicitly described in terms of diagrams. I'm going to give you a description. The description is actually easier in the symplectic case than the orthogonal, so I'm going to start with that. Right, so let's start with the symplectic case. It's 2D, and we take R to be D plus 1. So for K less than or equal to D plus D over 2, define the element psi K in the Brauer algebra as follows. You remember this is the alternating idempotent, except that alternating in the symplectic case means invariant. So this corresponds to the identity representation in some sense. So this is a perfectly good element of the Brauer category, perfectly good morphism from D plus 1 to D plus 1. Then we define phi by the formula, oops, phi is the sum, K equals 0 to the integral part of n plus 1 over 2, AK psi K, where A is this coefficient. I mean there that n should be. And now the properties of this phi are as follows. First of all, if you have this phi here, you write it like this. Then if you put a loop on it, either above or below, you get 0. It is a quasi-idempotent. So if you divide it by d plus 1 factorial, it becomes an idempotent. That idempotent is the so-called Jones idempotent of this Brauer algebra, so it corresponds to the trivial representation. So although this algebra is not semi-simple, it's still the trivial representation does split off from the algebra. And the most remarkable thing of all is this fact here. I think it's fair to say that nobody had any idea that this was the case, that in this very special Brauer algebra, BD plus 1 of minus 2D, the idempotent corresponding to the trivial representation is equal to the sum of all the diagrams. You just take each of the diagrams from D plus 1 to D plus 1 and add them together with coefficient 1. It's a very remarkable fact. For R greater than or equal to D plus 1, the kernel of that map is generated by that item. In the orthogonal case, the idempotent defining the kernel is a little bit more difficult to define. So you need these elements here, which are very closely related to the alternating. Remember, the alternating box in the orthogonal case does have the property that this is 0. The special case of E0, the one that I spoke about, the alternating diagram. And here are some facts about these various EJ. First of all, you have this fact that if you put a loop on any one of these, you get 0. That's actually not very hard to see. See, if you put a loop there, you obviously get 0. If you put a loop somewhere else, then you can pull the loop around there and put it there, and you get 0 as well. They are quasi-idempotents. If R is greater than or equal to m plus 1, then the kernel of eta R is generated by these various idempotents. It is a fact that all of these, so you take effectively half of these, that all of these are in fact in the ideal generated by this one special one. So it is this idempotent which generates the ideal. In summary, what we've discovered about the orthogonal group is that the kernel of the map from the Brauer algebra to the endomorphisms of tensor space is 0 when R is less than the dimension. But if R is at least the dimension plus 1, then the kernel is generated by this single idempotent there. In a sense, completes Brauer's program from 1937. So I should mention that this applies to any field of characteristic other than 2. You obviously would expect some problems in characteristic 2, particularly in the symplectic case. Juin and Chaire have proved that. And of course, there are quantum analogues and super analogues of these results, which we'll see in a moment. Now, I should say that the proofs of both the first fundamental theorem and the second fundamental theorem in the above form have traditionally depended on knowing some other formulations which generally are proved using identities, such as the Capelli identities, which on the face of it have no connection whatsoever with the problem at hand. And so what I'd like to do next is explain how there are some algebraic geometric arguments which can be used to which can be brought to bear on this situation and actually yield both the first fundamental theorem and the second fundamental theorem. So we're going to do a little detour into algebraic geometry, and we'll see how the same argument in fact applies to the orthosymplectic Lie superalgebra, and we'll see also to quantum quantum groups and also quantum superalgebras. So we'll take the context to be as it's been. We write E for the endomorphism. Well, we think of it now not so much as an algebra, but as a space, an affine space of all linear transformations of V. And we define an anti-involution on it by this rule. And we note that G is the set of endomorphisms of E which satisfy this condition. Of course, that entails that they're non-singular. Now, E has a subspace which I'll call E plus. That's just the endomorphisms, which are I'll call it dagger symmetric. In the orthogonal case, it is actually symmetric. In the symplectic case, it's not quite skew, but it's this variety is isomorphic to the variety of skew matrices. And in the orthosymplectic case, it's more complicated. Now, since dagger is an anti-involution, it is always the case that if you take this transformation, omega of A is A transpose A, then that's always a dagger symmetric endomorphism. And omega from E to E plus is a quadratic map. That means it's of degree 2 in the variables. Note that E and E plus are both graded. Now, we write C of Y for the coordinate ring of an affine variety, and note that C of E and C of E plus are graded, as I just mentioned. Here is the main lemma. In a way, this is not the best way to present this, but I think it's the most efficient way. And in fact, one of the reasons why it's not the best way to present it is because, in fact, Ateliers' original argument for this contains a gap. And that gap doesn't appear so well here. But I want to maybe refer you to my paper with Ruben Zhang in Nagoya Journal, 2021. It's when we talk about the second fundamental theorem for the orthosymplectic. So there we use scheme theoretic language, and the difficulty that I just referred to comes out more transparently. So the lemma, which is certainly true. There's no problem with the statement. There's only a problem with the proof. it says the following. Suppose f is a polynomial function on matrices such that f of GA equals f of A for all G in G. So G, remember, is O of V or SP of V here, although the context can be broadened. Then the conclusion is there is an F in C of E plus such that f of A, so we have E, we have omega to E plus, we have this F here. We're saying that there is an F like this. Now, obviously, small f satisfies this, then f, or it satisfies the condition. So if f of A, f of omega A implies that f of G A is f of omega of G A, and G A omega of G A is A dagger G dagger G A, and this is trivial, so any function of this form obviously satisfies the condition. Now, what this comes down to, this is actually an algebraic geometric statement which says that you can send, you can basically extend certain functions to the boundary. So if you look at E plus non-singular, so I'll call it E plus naught, then this is just GLN or GLV modulo G, because G is the fixer of a non-singular form. So this space, the space, so E plus naught can be identified with the set of non-degenerate forms of the type we're considering, whether symmetric or anti-symmetric or mixed or whatever. And if you, and what this lemma is all about is extending a function from that space to the space of all forms. That's what this all comes down to. I just did the little calculation that I did for you there. Yes, now let's observe that the third formulation of the first fundamental theorem for G is that if you take a direct sum of copies of V, then take the coordinate ring of that space, then the invariant functions are generated by the quadratic polynomials, which are given by taking inner products. So that is the third formulation of the first fundamental theorem. So in some sense, this main lemma is a special case of the third fundamental, of the third formulation. Now, before coming to the proof of this first fundamental theorem, I want to give an indication of how it's used to prove the first fundamental theorem. To prepare for the proof, we need to point out some canonical identifications. We have, because we're given a non-degenerate form, we have an identification of V with the dual, and we need to be aware that the action of the of GLV on the dual space has this particular form, under this identification. We have a canonical isomorphism between the tensor square of V star and the endomorphisms of V, and that takes phi V tensor phi W to the map, which takes X in V to V times WX. So once again, we have an action here, and it's easily checked that the natural action on the tensor square of V star is, it translates into some sort of a skew conjugation on E. So if you now take any complex vector space and you define the symmetric degree R symmetric on that, it's not an algebra unless you're now art of theory, of course, but it's a space. You define it like this. So there's a difference, once again, between the orthogonal case and the symplectic case. In the orthogonal case, you have invariants. In the symplectic case, you have skew elements. Similarly, the exterior power, you have the reverse. So the symmetric and alternating powers of W are in some sense reversed in the two classical cases, and we'll see there's an analog of that in the super case as well. Now we have this epsilon flip, which we've seen before, which just interchanges these with the insertion of an epsilon, and then you have this equation that if you take the composition of epsilon star and tau on V star tensor V star, then you get this. So under this isomorphism, like psi star, this symmetric power goes to E plus, and the alternating power goes to E minus. Together they generate the whole of E. So it's a canonical GLV invariant decomposition. And to come up with a proof of the first fundamental theorem for classical and later super G, we want to come up with a formulation which fits into the technology we've developed. So statements that I'm going to prove, I have to tell you, of course, what kappa pi is. Now, kappa pi of some tensor is nothing but the product of the inner products, where you apply first a permutation of 2D, take a place permutation, and then pair them up. You pair up adjacent things. So I don't know whether I've drawn this in my notes. Yes, I do want to point out this, that you always have minus the identity in these groups. So in the orthogonal group and the symplectic group. So that means, and the minus the identity acts on the R of tensor power as -1 to the R. So that means that if you want invariance, you better have R even. And so that proves actually this first statement there. So let's take R to be even and take a linear form on t to the rv, which is invariant under G. Now, we're going to define a map psi L from the whole of the endomorphism space. Well, at first times, this is just the product of affine spaces for the moment, as follows. Psi L of A, B1 up to B2D is just L evaluated on AB1, tensor AB2, and so on. So you can see from this that the degree of psi L on A is 2D. To get this value, you are going to be multiplying together 2D elements of A. And the degree of L on the VI is just 1. It's linear in the VI. Another way of stating that is that psi L is degree 2D in E, and it's linear on T to the 2D. Now, for G and G, by the invariance of L, if you look at psi L of GAV, then because if you multiply, if you put a G in front of each of these, you get the same thing, then you can actually leave the G out. So for each bold V, you have one of these functions that occurs in the main lemma. Namely, you have a function which is invariant under G on the whole affine space of endomorphisms. So we conclude that there's a function FL, which is of degree D now, on E plus. The reason it's of degree E is because omega is of degree 2, so you have to multiply the degrees there. And you have this equation. And this is true for all V, and for all A, of course, as well. And the key point is that FL is invariant under GLV. That's actually very easy to verify. It's a straight, that's not a deep fact. That involves just those identifications that I spoke about. Oh, I've apparently got a proof here. So if G is in GLV, then you have this, and so you've got F of that, and that, yes. So you see, you have to use the exact form of this G hat. So FL of G omega X, GV is equal to that, which is equal to that. And since the elements omega of X are Zariski dense in E plus, it's something which you need to check. I can come back to that if anybody wishes me to. We've got that this equation holds because it holds on a dense subset, and the function is defined in the whole space, that this is true. This is a justification of why omega X is Zariski dense. So to summarize what we've done so far is we've started off with an invariant functional on an even tensor power of V, and we've produced from that a function FL, which is invariant under GLV, which is degree D in E plus and degree 1 in these variables. So another way of putting that is that C to the D, the degree D polynomials on E plus, the same thing as the degree polynomials on S2 V star, and that's the same as this. This canonical map, which takes you from T to the 2D of V star to S to the D of this, induces a canonical map which commutes with GLV from C to the D E plus to T to the 2D V star all star. And remember, this is all invariant under GLV. So what we've produced is a canonical map from this space here. So in summary, and this is the takeaway, we have a map from which has taken us from an invariant linear form to a function HL, which is invariant under GLV, and a function on this space which is invariant under GLV. We're just parenthetically remarking that we got to this space through there. And this map has the property that if A happens to be equal to omega x, then HL of big tensor product of A's and V is equal to FL of AB, which is equal to psi L of XV. So in particular, if you take A to be the identity, which is the identity dagger identity, then this is equal to L of V. So the map from taking L to HL is injective, because you can recover L from HL. To take home, we have an injective map from the invariants here to the from the orthogonal or symplectic invariants there to the GLV invariants here, and that is the key to understanding the fundamental theorems for the classical groups, because we use this to, together with our knowledge of the GLV invariants on here, to make deductions about the space that we're actually interested in. So this space here is spanned by the maps H pi. We've seen this before. H pi of this is equal to the pi's in the symmetric group of degree 2D. So we permute the elements of the tensor, and then we just take this product. If you apply this formula to this particular case, then you get just this kappa pi, which we saw before. Now, I should point out that this kappa pi can be thought of as nothing more than a way of pairing these elements. If you write the tensor, the elements of the tensor down there, you just have to say which one is paired with which and in what order, and this is exactly what happens. One consequence of this is that because the space into which we're mapping our invariants is spanned by these, it follows that L has to be a linear combination of the K pi. It's going to show now how the injective map to prove the second fundamental theorem and orthosymplectic groups. First of all, want the diagrammatic formulation of the second fundamental theorem. So diagrams from 2D to naught in the Brauer algebra look like this, and they can be therefore identified with partitionings of 1 up to 2D into pairs. The first fundamental theorem says that there's a surjective map from B0 2D to the invariants of G of this isometry group on the tensor power T2D of V. Not the invariant elements, the invariant functionals. We can do it either for the dual or the space itself. And is given by D goes to KD or kappa D, where kappa D is given by this. Now, there is a small ambiguity, which people may have noticed in the symplectic case, where you have to be a little bit careful about the order in which you take these pairs, VI and VJ. And in the orthosymplectic case, there's an even further ambiguity, because when you multiply these together, you need to be careful about the order in which you do that as well. But I'm going to put that aside for the moment. The second fundamental theorem identifies the kernel of kappa, which is the map which takes diagrams like this into endomorphisms. Symmetric group of degree 2R acts transitively on the set of diagrams in B2D naught by right multiplication. And let's take D naught to be a special diagram, namely this one. The stabilizer in the symmetric group is just the stabilizer of the involution 1, 2, 3, 4, and so on, up to 2D minus 1, 2D. So it's got order 2 to the D times D factorial. So every diagram can obviously be expressed as D naught pi D, where you put this D naught first, and then under the line, you have any permutation that you like. That element is going to be unique up to pre-multiplication by an element of the stabilizer of D naught, which is the group I've called C. Here's how that picture looks. There's D naught on top and a permutation at the bottom. Now, we also have delta from B 2D, 2D to the invariance of GLV on there. You don't need the whole of the Brauer algebra. You only need the permutations in it, but that's all right. We still have the map. The others can be taken to 0. They form an ideal anyway. Yes, so delta pi of this. The key idea in this geometric proof of the second fundamental theorem is that there's a commutative diagram, as we show here. We've seen most of these maps before. Delta we just saw, kappa we just saw. H is this map which takes L, that's to an invariant of GL. And the only one we haven't seen is chi. So there is obviously a map chi which makes this commute. So what is that map? And remember, H is injective, that is a key point, and these maps are surjective. The horizontal maps are surjective. The map chi is given by taking a diagram to idempotent corresponding to the stabilizer C times, so in other words, if you have a diagram like this, and here you have a permutation, then all you do is you interpose here, B of C. I claim that this makes this diagram commute, and it makes the whole situation look absurdly I think what we'll do today is just draw the following conclusion, that the second fundamental theorem can be characterized. We need to understand the kernel of K. So if you look back at that commutative diagram we had, the kernel of kappa is the same as the inverse image of the kernel of delta. So what we need, we're reduced to a problem in the invariant theory of GLN. And so that is just d naught of the kernel of delta. The kernel of delta is known. It's just generated by this alternator that's in this easy case. It's more complicated in the orthosymplectic. And so we know exactly what it is. So a typical element of the kernel of K is just something like this, where theta is this alternating rectangle. And by the way, it incorporates the this idempotent E of C already. That's why you don't see it here. For example, in the orthogonal case, I think we're running actually a little bit short of time, so I think I'm going to stop there. So this is, we've gotten to the statement of the second fundamental theorem, and I'll just explore that a little bit to relate it to known results. And next time we will explore further how these ideas can be applied in a more general context of supergroups and quantum groups. And thanks very much for today.